So let's welcome Subhrata Dey, that is a postdoctoral researcher at National Center of Nuclear Research. Subhrata did her PhD in Krakow at Jagiellonian University, and before that she graduated from Bangalore University in India, and she's working, during her PhD she was working on some set modeling of bright galaxies, and that will be the topic of her talk today, so the floor is yours.
Thank you. Good evening, everyone. Thank you for hosting me, Milena. It's a great pleasure to give a talk here. Very beautiful building. So this is part of my PhD thesis that I defended in October 4th. So in Jagiellonian University, and my supervisors under supervision of Professor Michał Ostrowski and Arti Goel. And of course, in collaboration with a lot of other people here, you can see Katarzyna Mawek at NCBJ, and then Krzysztof Fiji from UJ as well, Jagiellonian University, Agnieszka Polo, Marek Emrozi, etc. So this project wouldn't have been possible without their contributions. So I'm very thankful to them. So, okay, I think I have to go here. So this will be more or less the outline of my talk. I'll just try to give you a brief introduction of what ultra-luminous, or luminous infrared bright galaxies are, what SED modeling is, about the UV-IR radio SED modeling of 11 LIRGs, continued by 14 ULIRGs, and then results and discussion of the global astrophysical properties of 25 ULIRGs. And then we'll move to the conclusion. So in 1980, when the infrared astronomical satellite was scanning the sky, it came across few galaxies which were too bright in the infrared but were missed by the previous optical surveys. So these galaxies were classified as luminous or ultra-luminous infrared galaxies. So as you can see, the luminous infrared galaxies has infrared luminosity between 10 power 11 and 10 power 12 solar luminosity. And then we have ultra-luminous infrared galaxies, ULIRGs, with luminosity greater than 10 power 12 solar luminosity. So, of course, it's an important question to ask, what is causing such high infrared emission? So, there are two major candidates. The infrared emission is because of the warm dust that is heated by the AGN. So, the torus surrounding the AGN is heated and that is emitting the infrared emission. Or there's a massive burst of star formation which can happen either due to merger or just in galaxies having massive burst of star formation, which is, again, the UV emission is absorbed by the dust and re-emitted in the infrared. So these are the two major candidates for the infrared emission.
We don't share the screen as well.
We did share the screen. Okay, sorry. Okay. Now it's okay?
No, yeah, it's fine.
Okay, sorry. Sorry about that. No. Okay, so talking about ULIRGs in context of galaxy evolution, what you see here is the famous Madhau's plot. So you're seeing here star formation rate density with respect to redshift here. Or at the, I'll just hide this. Yeah. At the bottom, you have the age of the universe. So this is us here, and then this is from the Big Bang, let's say. So here in the dotted line, dashed line, you see the star formation rate density. And the star formation rate density is estimated from various compilation of UV and IR data of star forming galaxies here. So you can see that the star formation rate density increases, peaks at around redshift 2 here. I'm sorry, rather I should go this way. Peaks at around redshift 2 here, and then it declines. What you also see here in the black is the black hole accretion rate, which is obtained from the X-ray emission. So the black hole accretion rate also kind of peaks at around redshift 2 and then declines further. So the point here is that we see that the SFR and black hole kind of show some co-evolution here, and which is an important factor thinking about the galaxy evolution. So now, when we break this part by luminosity class distribution, we see that LIRGs and ULIRGs play a very important role. So LIRGs and ULIRGs having minimal influence at the low redshift kind of increases its contribution at the high redshift part around the same epoch of 2. So this kind of tells us that these galaxies are very important to study the galaxy evolution here with galaxy black hole co-evolution. And then so combining the information about galaxies, LIRGs and ULIRGs being powered by AGN or massive burst of star formation, Along with its contribution to this epoch that we saw here, it puts the point that ULIRGs are very important important for us to study in order to understand how galaxy evolution happened. So considering that galaxy evolution from a part of merger of gas-rich to red-ended one, ULIRGs place themselves at a very important point, in important stage in point of galaxy evolution. So now talking about spectral energy distribution, let's say we have galaxies with a lot of stars, we'll have in the spectral energy distribution a lot of UV and optical emission. So just to tell you, spectral energy distribution is basically flux over wavelength, how we see the spectra. So then if we have dust in the galaxy, what we'll see is the emission from the stars, the UV and optical emission from the star is absorbed by the dust and then is re-emitted in the infrared wave band. Then if you, let's say the galaxies has lots and lots of dust, as in case of LIRGs and ULIRGs, so there's a decrease in the optical and UV, so this part is called attenuated, and then there's an increase in the infrared wave band. So this tells us that, dust makes it a little bit difficult for us to study the energetic part of these galaxies directly, because it's kind of not letting us study the star forming part of the galaxies. So here, radio continuum comes into rescue. So what we see is radio emission remains unaffected by dust extinction and gives us the direct view into the energetics of the region. So just talking simply about radio continuum, it basically has two parts. The synchrotron emission. Synchrotron emission is just the acceleration of these electrons in the presence of magnetic field. So this is in star-forming galaxies. If you have, stars ending up as supernova, they will accelerate the electron, and in presence of magnetic field, we will have the synchrotron emission. And then we have free emission, as you can see here. So free emission is basically in these gases, the ionized gases of the ISM, interstellar medium. There are these electrons, when they come in this contact of this ionized medium, they get accelerated. And then we have the free emission. So if you can see this is kind of the spectra of the SED of the radio, and you can see that both of them have very distinctive nature. So free has a slope of minus 0.1, whereas synchrotron has around minus 0.8. However, we see that radio SEDs are not that simple, as it's always being assumed that there's generally power law in nature. But what we see is they are complicated by various absorption processes. So the two absorption processes that majorly influences in this radio SED are synchrotron self-absorption or thermal free absorption. So synchrotron self-absorption, in a simple way, the synchrotron emitting population of electron that reabsorbs this emission, and then we have this attenuation that we see, absorption in the SED. Further, what we also have the thermal free absorption. So this is just attenuation or the absorption of the free emission by the star-forming region, the ISM of the galaxies. So just to tell you about this is a very beautiful plot created by Misha. So when we just focus on, let's say, one wavelength, we miss on a lot of important factors. We are biasing ourselves to a particular property of a galaxy. However, the panchromatic study or the multi-wavelength study of a galaxy is very important to understand all the physical processes that are happening in these galaxies. So just to give you an understanding that we can see that the UV traces the young stars, the visible near infrared evolved star, the mid and far infrared again traces the dust and the hot dust, the submillimeter traces the cold dust, and the radio, which gives us the direct tracer of the star formation. All this together are very important for us to understand the complete nature of what galaxies are going through. So now I'll discuss about the UV-IR radio SED modeling. So now I'll present you the results of my first paper, which was focused on studying 11 LIRGs, luminous infrared galaxies. So here, so the sample selection was based on this criteria that the luminous infrared luminosity is greater than infrared luminosity is greater than 10 to the power 10.75 solar luminosity, and they were selected from this Condon et al. 1996 paper. Also, with the flux density greater than 5.24 Jansky at 60 microns. So these are characteristics of LIRGs, basically. And again, important because we wanted to study the radio SEDs, it's very important for us to have observations. So we made sure that the counterpart exists in the TIFR GMRT telescope. So there's a telescope based in India, radio telescope based in India. So, and our main aim was to observe these galaxies with these telescopes at different frequencies. So these are the list of the 11 galaxies that you see here, very nearby galaxies, because our main aim was to study nearby galaxy, understand their property like in thoroughly so that we can move on to the further high redshift galaxies. So this was the dedicated observation done by Aarti, my supervisor. I did not join my PhD then, so it was much later. But during her postdoctoral tenure, she observed these galaxies at 325 and 610 megahertz at using the GMRT telescope. Further, I collected the archival multi-wavelength data. So I had data from VLA at 1.4, 3, 4.8, 8.4, and 14.9 gigahertz. Then this is again in USA, New Mexico. Then we had GLEAM, which is based in Australia. I had low frequency data from 70 to 300 megahertz, along with ATCA, SUMS, Effelsberg, etc. So we could generate a broadband radio spectra from 70 megahertz till 15 gigahertz. Now discussing about the radio-only SCD model. So here is a list of very simple single component radio SCDs, such as the synchrotron free emission, or free absorption. However, in some studies like this, Clement et al., they saw that, I'm sorry, while studying these massive starburst galaxies such as LIRGs and ULIRGs, they saw that the radio SCDs are not that simple. They see that there is some kinks here. So there is a low frequency turnover, and then the mid frequency, that is around 8 gigahertz, they have some flattening there. So they wanted to understand what exactly is happening. So then they developed further models. So these models are based on star forming region in the galaxies, either having different orientations. So either you view them edge on or like face on, or having different composition that is defined by the spectral index. So star forming region having different electron population. So the different orientation here is defined by the optical depth of the galaxy, and different electron population will be defined by the different spectral indices. So total like this, here are just 2 examples. So we had total 8 models with which we were modeling our galaxies. So here you can see now I have galaxies, I have all the data available. So my main aim is to do the fit the models. So we had 8 models. Now each of the data was fit with 8 models, and then here is the best fit model. That is for this galaxy, ESO 440 IG058 and ESO 507 G070. We have synchrotron free emission with absorption and synchrotron free emission with absorption power law. Just to show you that these galaxies are just not simple power law as was always thought, but rather have a low frequency turnover. And I used Ultra-luminous Bayesian inference package for the model fitting and model comparison. And here there are results of a few more galaxies that we have. So you can see hardly some of the galaxies have power law. Majorly have either low frequency or mid frequency turnovers that you see. Also to point out here, so initially when we were just doing simple curve fitting modeling, we couldn't decompose the total radio continuum into thermal and free and synchrotron. But here, because of using Bayesian modeling, we could decompose the total synchrotron into this thermal part, as you can see here, the free emission. And here, this is the non-thermal part, the synchrotron emission. I'll tell you why it's important in few slides. So just to take away the main key points here are radio-only SCD modeling show complex shape with single or multiple turnover in case of LIRGs, with power law rarely characterizing the spectra. And here, of course, the thermal turnover is due to the thermal free absorption. We say that because our galaxies are first strictly star forming. And when we see that the synchrotron self-absorption is mostly happen in the cases of AGN. When galaxies have AGN, radio AGN, there we see more cases of synchrotron self-absorption. So these are the results, radio-only SCD modeling here. After modeling, so here the A and C defines the non-thermal normalization component. That is what you, this part, the non-thermal normalization component. And then the B and D represents the thermal normalization component. That's this one. So these are important to estimate the respective star formation rate. So now we had the UV IR archival data. So I gathered UV data from GLEAM and XMM Newton, then optical data from Pan-STAR, Dennis, and then these are all either space-based or ground-based archival data. There were no personal observations done. And with that, again, you have the UV archival data. This is how the points would look in the SED. But how to model is using, what we use is SIGAL. So SIGAL is basically a code for investigating galaxy emission. It works on the principle of energy balance. That is, the energy that is emitted in the UV IR is reabsorbed by the dust. So SIGAL is very modular, as you can see. So it has this star formation history, and stellar population is modeling the UV optical part. Then you have attenuation and dust together with the star formation. You can see that there is an attenuation part here, and then re-emission in the infrared. And then we had the nebular emission. So this is just to give you the glimpse of how SIGAL works. So with all those modeled together, we get this total SED from the UV to IR part. Now, SIGAL recently also included the radio module. So you can see that this is the UV IR part, what you see here, and this is the radio. So here you can see SIGAL is only including a power law. But I just discussed in my previous slides that the radio SED modeling are not just power law, but rather have a complex feature, maybe low frequency turnovers or mid frequency turnovers. So that was, this was just to have a check of what exactly is happening when we include the radio SED, radio fluxes as well. And to our astonishment, it was quite interesting that inclusion of the radio data to the UVIR SED significantly improved the accuracy. So it reduced the dust luminosity and SFR uncertainty by 0.2 and 0.3 dex. So this is something good. That what I'm trying to tell you is that dust luminosity and SFR is very well constrained when we are including the radio module here. So this is good news for us, because as we know that we have a lot of plethora of data from SK and its precursor telescopes, and very few infrared telescopes coming up. So with that, even with less data, with radio data, we will be able to constrain the dust luminosity and SFR very well. This is just to show you how the UVIR SED modeling looks like. So what are the results that we get? So we have stellar mass, dust temperature, star formation rate, etc. So these are different estimates of the modeling that we get. And just to point out that our galaxies were strictly majorly star forming, because AGN contribution was hardly 7% here. So just to study the star formation rate with galaxy properties. So here you can see a plot of star formation rate with respect to dust. So there is very known correlation of star formation rate with dust mass, because the more star formation we have, the more dust, this high mass silicon and others will be ejected into the dust particle into the ISM of the galaxy, and then we see a very straight correlation. So our point here was just to see if what we obtain is matching with the literature done. So we can clearly see that our galaxies are behaving similar to the galaxies of same classes as studied in past. Also, we had the star formation rate infrared with the stellar mass here. So again, the stellar mass, the more star formation, the more stellar mass. But then at the point, there is this flattening that we see, because after certain mass, there is no more star formation happening. And here also, we saw that our galaxies are the results are more or less corroborating with that of the other studies done. So this is rather, I would say this is just a sanity check of our studies. So with the past, whatever is done, if our results, what we are obtaining are making sense or not. So this is one of the most important part of our study in this paper is the calibrating radio SFR. Just to remind you that radio remains unaffected by dust. So it is helping us to study the energetics of this galaxy as and when they are happening. So here, what you see in this plot, in the y-axis, you have star formation rate estimate from SIGAL, if you remember, averaged over 100 megayears and averaged over 10 megayears. So from us, 100 megayears averaged SFR, and then 10 megayears averaged SFR. So this is UVIR part of the SFR estimate. What you see here is the total thermal and non-thermal. So if you remember this plot, so the total comes from the black, so total radio emission. We had the SFR estimated from the total radio emission, the non-thermal or the synchrotron emission estimated from the magenta part at 1.4 gigahertz, and then we have the thermal emission. Why this is important? Because again, here when we are studying the thermal emission, we are directly tracing the star formation. But here, it's not a direct tracer. Here, from the star formation, the emission is absorbed by the dust and then re-emitted in the infrared. So here we are getting a direct information of how the star formation is happening here. So, sorry. Yeah. Another point to notice here is this P, the P that you see. So when the P is less than 0.01, we say that the correlation is significant here. So you can see that here in this plot A and B, panel A and B, there's a strong correlation, but we don't see anything in the 100 mega years, 100 mega years estimated SFR. So now, to understand the radio SFR, the total and non-thermal SFR, shows very strict correlation because these galaxies, normal star-forming galaxies, the magnetic field is of order of 50 microgauss. So in that, the synchrotron lifetime, that is the age of the synchrotron emission, is around 3.3 into 10 power 6, which matches with these two. So that kind of explains why we are seeing a very strong correlation here between the 10 mega years and the total and the synchrotron emission. So key takeaway message here is synchrotron emission is an effective indicator of recent star formation because 10 mega years is representative of recent star formation happening, and total and synchrotron or non-thermal is very well correlating with that. Now moving on, moving on to next one. So here we studied the ULIRGs, that is ultra-luminous infrared galaxy. Now, this ULIRG sample was quite interesting for us because if you remember in LIRGs, I told you they were majorly star forming. Major emission from the galaxy, the radio or the infrared, was from the star formation part. But here, some of the galaxies have GPS type AGN. By that, I mean that they have very young AGN jet formation in these galaxies. So these galaxies have started forming the radio jets, but they're very young. So this was quite important for us to understand what are their contribution to the radio SEDs. So again, we gathered data from 54 megahertz to 33. We had more data here till 33 gigahertz from all these surveys that you can see. Again, we saw that the SEDs are not very simple power law, but rather more complex here. Some more examples of the SED that you can see here again. So what we saw is there's no significant difference in the complexity of the radio spectra in ULIRGs and LIRGs, despite more interaction signature in ULIRGs morphology. So by that, I mean our LIRGs had a sample of non-merging and merging galaxies, but ULIRGs were majorly interacting or merging. And we did not see any signatures of we did not see like ULIRGs having more complex SEDs compared to LIRGs. They were, both of them were having similar, by percentage, they were having similar nature of radio SED. So here is the UV-IR SED that you can see here of UGC 8058 and 8696. So here, important thing here, SIGAL also includes the radio loudness. By that, I mean it tells the what is the contribution of, let's say, AGN, radio AGN to the galaxies. So you can see here, the orange part is the AGN part of the galaxy, which extends till the further till the radio part, and we could decompose the radio SED into the AGN part and the star forming part here. So the maroon color shows, not very visible though, shows the star forming contribution to the radio SEDs. This will be important because I'll tell you why. So these are again the SIGAL SED results, and you can see here that some of the galaxies have very high AGN contribution, so which is like 99. So this was basically a quasar. It qualified as a ULIRG because it was a quasar. So its infrared emission was majorly coming from the dusty Taurus part of the galaxy. So now coming to the overall discussion, because we use the same methodology and throughout both the studies, so we could compare their results, which was good. So we had 25 ULIRGs total, and we wanted to discuss their global properties. So the first is the thermal fraction, which is the radio thermal fraction. So thermal fraction is basically at 1.4, what is the thermal emission that you have divided by the total emission. So that is thermal fraction. Why thermal fraction is important? I'm reiterating because thermal fraction, the thermal emission tells us when the galaxy, so it's a tracer of interstellar matter in the galaxy. So the emission is from the star forming region directly. As in when the star formation is happening, the UVA emission is ionizing the gas, and then in that gas we get the free emission. So that is what is important. So we see here. So we see here that the triangles are the LIRGs, the stars, here you can see, okay. So triangles are non-merging LIRGs, the stars are the merging LIRGs, and then the circle are the ULIRGs. And our expectation was, since LIRGs have more ULIRGs have more star formation happening, there'll be more ionizing radiation for the gas, and then we should have more free emission. The ULIRGs should show more thermal fraction compared to LIRGs. However, we are seeing that ULIRGs and LIRGs show similar range of thermal fraction, which was around 0.05 here. So this was quite interesting. So our hypothesis is why ULIRGs show same range of LIRGs is because in ULIRGs you have more dust. So now this star formation, as and when it's happening, the UV emission is surrounded by dust. The dust is reabsorbing the ionizing photon from the stars. So there's not enough emission, the ionizing photon available for gas to get ionized and to have further free emission. So that is one of the reason that we are seeing that ULIRGs having similar nature of thermal fraction as compared to LIRGs. Also, what you see here is this one galaxy, which is way above out of the scenario here. This is because this, again, if you remember, I said it's a quasar. So this it qualified as a ULIRG because of its emission from the torus of the Aegean. So that tells us the host galaxy did not have enough dust. So hence the thermal fraction is quite high. That is, gas ionizing fraction is quite high, and then we can have more thermal fraction and thermal emission, and hence the thermal fraction is quite high here compared to any of the other galaxies. So now talking about the infrared radio correlation. So in 1992, Condon studied just simple star-forming galaxies. Here the plot is of 1.4 luminosity, 1.4 gigahertz. That is the radio tracer with respect to far infrared tracer, far infrared luminosity. And they saw that there is a very strict, beautiful correlation between the radio infrared part. So in a simple term, so when this OB stars, they have this dust surrounding it, right? So the OB stars heats the dust, and from there we have the infrared emission. These massive OB stars also have the supernova explosion, from which the electron accelerate, and in presence of magnetic field, you have the synchrotron emission. So there's this, the source of this emission is more or less the same. Hence, we are seeing a similar straight correlation between the two. So we also tried to study how our galaxies are falling in this perspective. So QIR is the infrared radio correlation. In the red, what you see there is the normal star-forming galaxies studied in the Yoon et al. 2001. The triangles there are the non-merging LIRGs. Again, the stars are the merging LIRGs, and you can see that they are more or less behaving in a similar nature with respect to Yoon et al. So they are strictly star-forming. However, the ULIRGs is showing quite interesting character. They're spreading all over the plot. So this is because some of the galaxies are a bit radio loud here. As you can see here, radio loudness. So they are radio loud here, and hence they are falling just below. So the point of this plot is just to show you the nature of the galaxies that we have here. So they're just not star forming, but some of them are radio loud in nature. Indicator of an Aegean there. Now, you might ask that, okay, if they're radio, how do you know that the SED that you had, the emission is from Aegean or star forming? So one way to trace that is via the thermal brightness. So we studied the brightness temperature of these galaxies, and we saw that most of the radio emission is from the star forming part of the galaxies, not from the radio part. So again, coming back to the calibration of SFR at radio wavelength. So here it's SFR IR versus 1.4, SFR radio 1.4, if you remember in the LIRGs paper. So here we have again the LIRG sample along with the ULIRG sample here. And so if you remember again the p-value, here you can see that this tells if the correlation that we see are significant or not. So here we saw that, I'm sorry. Yeah. So if you remember in the LIRGs, we were seeing just correlation with 10 megayears. But here, interestingly, we see a correlation both with 10 megayears and 100 megayears. So this kinds of tells us that ULIRGs, by its nature, since they're mergers in nature, mergers most of the time, so they are undergoing multiple episodes of star formation. Hence, we are seeing that the episodes are like 10 megayears and 100 megayears. We are seeing a strict correlation, infrared correlation with the total and the non-thermal radio emission. Now, since we had data, we also tried to understand the star formation rate at 4.8 gigahertz. So this was quite interesting for us because that is the first time that we are seeing now that even the thermal is showing some correlation here. So if you remember till now in the LIRGs and even in the previous plot, the thermal emission was not showing any correlation with the SFR-IR. Mostly our hypothesis is because of not well constrained thermal emission probably in the modeling part. But here we are seeing with 4.8, we are seeing a strong correlation. So you can see here that the p-value is low again. So talking about the synchrotron part here, so synchrotron lifetime are about a factor of 2 smaller for electron emitting at 4.8 compared to 1.4. That is, the synchrotron emission at 4.8 is dies down much more earlier than the at 1.4. So hence we are seeing a very strong correlation at 10 megayears compared to 100 megayears here. Then talking about the thermal part, now if you see that the thermal emission has a spectral index mostly of minus 0.1. So if we study at 1.4 or 4.1, there shouldn't be much difference in the thermal emission there. More or less they are standard. But here the important thing to notice is that at 4.8 gigahertz, the optical depth of these emitting star forming regions is less. By optical depth, I mean if they are more compact or rather this thing. So the thermal emission is at 4.8 is correlates well with infrared SFR infrared averaged of 10 megayears because the nature of the optical thin 4.8 gigahertz emission. So this is interesting that thermal luminosity at 4.8 gigahertz is a better indicator of recent star formation compared to 1.4 gigahertz. So since we did the modeling, we also wanted to study the nature of the radio-derived properties such as the alpha, such as the radio spectral index with the UV-IR SED modeling, such as the redshift, SFR-IR, stellar mass, SSFR, and M-dust. And we saw no statistically significant correlation, even though there's scientifically some processes that should technically correlate. So our guess is because our sample size is low, probably we do not see any statistical significant correlation here. If you want to know the science part of how they are correlating, I'll be very happy to discuss with you after the talk. So now just moving to the conclusion. So what we see, radio-only SED, there is no significant difference in the complexity of the radio spectra in ULIRGs and LIRGs, despite showing more interaction signature in the ULIRGs morphology. The thermal fraction in ULIRGs and LIRGs are similar, likely due to dust absorption of ionizing photon. The inclusion of the radio data in the UV-IR SED modeling improves the dust luminosity and SFR estimate by an order of magnitude, which is good news. The SFR calibration total and non-thermal radio luminosities at 1.4 are reliable SFR indicators for LIRGs and ULIRGs. Again, the thermal radio luminosity at 4.8 gigahertz is a better SFR tracer compared to 1.4 gigahertz due to optically thin free emission at this frequency. Finally, the modeled non-thermal spectral indices do not show any statistical significance correlation with redshift, stellar mass, dust mass, SFR, SSFR. Thank you.
Thank you very much. Thank you very much. Do we have any questions or comments? I actually have a question about the temperature. When you modeled the LIRG,
Yes.
there was one of the parameters that you get from the set modeling was the temperature of dust.
Yes, that's right. Dust
and
temperature.
The errors were pretty small. So is it normal that you get, I mean, such precise?
I think so because we had very good infrared coverage, infrared dust, photometry. So that could be the reason because eventually to check if the estimation are robust or not, we have the PDFs as well to see if there's degeneracy or something, and they were all single peaked. This was one question asked by a reviewer as well in the paper. So,
I didn't read the reviews.
No. So this
As
is
well, because it's surprising. I mean, to see
Yeah,
well,
indeed.
still like quite a lot of
yeah.
the error bar seems small with all, yeah, almost all of the parameters.
Yeah.
Okay, but makes sense. So, any more questions? So I will ask one more. A LOFAR would be useful. LOFAR.
I did use LOFAR for the ULIRGs.
Okay.
For LIRGs, because they were all in the southern declination, and LOFAR only observes the northern part of the sky. We did not
Okay.
have LOFAR data, but for ULIRGs we had LOFAR data.
And
as
for
well.
the southern one, could you use something similar in the same frequencies?
Yes, so we used GLEAM, that is the South
Okay.
Australian one, which
Okay.
covers the similar range.
Okay, so
But
it's-
LOFAR is good, much
and-
better, I would say, than
LOFAR is better, right?
Yeah. With resolution. It's much better than any of the available radio telescopes in the same frequency range.
Okay.
Yeah.
Because I know that Jagiellonian University is active in
Yeah,
LOFAR, right?
Shishtok is, yeah.
Yeah.
So, but there were no our observations, they were all again archival. Yeah.
That's good.
That is LOFAR, LOLs, that is the low.
Okay. So, let's see. And that's the
54.
10 to minus.
So it's like around 54
megahertz.
megahertz. Yeah.
Low. Anything on Zoom?
No, I don't see any
No questions?
questions there.
If not, so let's thank.
Thank you. Thank you for being here. Thank you.
Thank you. And next week, Michał